inaugurated this online lecture series in the backdrop of the pandemic in 2020. The fundamental objective of this series is to engage and enrich the knowledge of undergraduate, postgraduate, and doctoral students specializing in statistics and related fields. Eminent statisticians from India and abroad have previously delivered lectures eliciting a positive response from students and researchers. With great pleasure, I introduce Dr. Abhra Sarkar, who joins us as an honored speaker to you today. Dr. Sarkar, an associate professor at the Department of Statistics and Data Science at the University of Texas at Austin, has made remarkable contributions to Bayesian semiparametric and non-parametric methods and numerous applications in neuroscience, nutritional, epidemiology, dietary health, and consumption pattern clinical trial design. Dr. Sarkar started his journey with statistics from Narendrapur Ramakrishna Mission, followed by post-graduation from University of Calcutta, doctoral research from Texas A&M University, USA, and postdoctoral research from Duke University, USA. Dr. Sarkar has authored and co-authored an impressive array of scholarly articles published in top-tier journals such as the Journal of American Statistical Association, Biostatistics, Biometrics, Scientific Reports. A recipient of several prestigious awards, including the Michel Prize 2018 and 2020 from the International Society for Bayesian Analysis, and student paper awards from the International Indian Statistical Association and American Statistical Association. Dr. Sarkar's influence extends well beyond academia. His research has been supported by major funding bodies such as the National Science Foundation, the National Institutes of Health, affirming his leadership in addressing the most pressing challenges in statistical theory and application. In addition to his research, Dr. Sarkar is highly regarded as a mentor and educator. He has supervised many PhD students, guiding them to become leading researchers in their own right. His commitment to pedagogy, as evidenced by his courses on advanced Bayesian methods, has cultivated a generation of statisticians equipped to tackle complex real-world problems. Moreover, Dr. Sarkar has served on the editorial board of esteemed journals, further contributing to the advancement of statistical knowledge and practice. We are most fortunate today to be graced by Dr. Sarkar's presence and to benefit from his deep expertise. Please join me in welcoming Dr. Abhra Sarkar. Over to you, Dr. Sarkar.
Thank you, Subrata. Let's see if I can share my screen. So I tested this before. Can you see my screen now?
Yes, it is visible.
Okay. Well, thanks for the invite. I wish I could be there in person. I have not been able to visit India actually since 2019, since before the pandemic. Well, thanks for the nice introduction, Subrata. It was a little long, I'd say, and I felt a little awkward coming all of this from a former classmate. But anyway, I'm honored to be here. So I'm going to talk about Bayesian semiparametric local inference and other stories. Again, Subrata, can you confirm that you can hear me clearly?
Yes. Yeah, you are completely audible, clearly audible.
Okay. So given the nature of this series, I thought about preparing the slides slightly differently, maybe just highlight some of the interesting applications I have worked on over the years. But then this has been a brutal semester, and in the end, I decided to just go with the lecture that I'd given in my own department a few weeks back. But that was well appreciated by the students, so hopefully this will go well as well. We'll see. So this is how I define the problem of local inference. So we have a response variable yes, and some associated covariates x1s, x2x, all the way up to xps across some space S. And the idea of local inference is that we'll assume that different sets of predictors can be important in different parts of S. And also importantly, the same predictors can be differently influencing our response Y in different parts of S. So if you look at the figure here, so this amounts basically to constructing a partition of S such that in different parts of S, the behavior, the relationship between Y and X would be different. Different sets of predictors can be important in different parts. For example, in the other figure, figure B here, we see there are two different regions where X1 is important, sort of like the orangey regions. And there are two also regions where two variables X1 and X2 are important. It is possible that the regions where the same variables are important, they would be adjacent to each other, but their influences are still different. And there is one region here on the right-hand side, S3, where X1, X2, and X3 are important. And here it is also possible that the original set of predictors was a bigger set. For example, it is possible that in this case we had started with X1, X2, X3, X4, X5, but X4 and X5 were not important anywhere in S. So that's the whole idea. Additionally, for most applications, it would be plausible to assume that this influences very smoothly across adjacent parts of S. So here in the figure, S2 and S4, even though the same variables X1 and X2 are important in there, their influences are different, but still probably similar to each other. And for this talk, all the examples that we'd have, we'll consider the case when X1, X2, XP are categorical. And the support of X over the entire space S, that doesn't vary. So they take the same values basically across the entire domain. And then the problem we'll see then reduces to basically constructing dependent partitions of the set of possible values of X at every S, or if S is a very big set or a very dense set on a grid on S. The fact that we have categorical variables here, that's not necessarily a simplification of the problem. Unlike common perception in statistics, categorical variables are often much harder to deal with in a principled way. We'll see some examples. But then the literature on this problem is really extremely sparse, especially non-parametric treatment of this problem. So in that sense, it's a nice problem to look at, which has received very little attention, but it's very important, very broadly applicable across many domains, as we'll see. So I'm going to start part one now. So here I'm going to assume that Y, our response variable that I talked about, is a continuous response variable, and it varies longitudinally over time. So this set S that we had here, script S, this basically denotes a time window. And then again, we have associated categorical predictors. For simplicity, we'll start with a single categorical predictor X, and X may or may not vary with time. In this particular case, we will assume for simplicity it doesn't vary. So the methodology is broadly applicable. Methodology is quite general. If X varies with time, that is also still okay. But we'll assume that X stays constant across time. And then again, the idea of local inference tells us that levels of X may affect Y differently in different longitudinal states. So you're going to model this like this. So we have YILT, I for the, so throughout the talk, I'm going to use I for the subject. So I subject, T for the time point here, and L would be for basically replicated observations or trials and things like that. So you're going to model the behavior of YI, the stochastic behavior of YILT by decomposing basically it into three different parts. The one is just the random error part on the right-hand side. And then there'll be fixed effects, FXT, functional fixed effects, which vary with time and also with associated predictor X. And then there are also random effects, CYT, which don't depend for simplicity again on X. So it's sort of like random intercept type term, but they do vary with time still. So here's an example of it's a synthetic example, simulated example of how local inference, might play out in scenarios like this. So we have our y, and we have 20 time points. And then if you look at the first 5 time points, that function fxt, it's constant across 3 different levels of x. So x here is a categorical variable that takes values 1, 2, and 3. But then something interesting happens at time point 5. The effect of 2 separates out from the effect of 1 and 3. So this is the branch for 1 and 3. This is the branch for x equals to 2. And then at time point 10, the effect of 1 and 3 further branch out from each other. And then finally at time point 15, the effect of 1 merges back with the effect of 2. And then they stay together basically for the rest of the time point. So it's a very organic framework. This functional mean fxt, it can diverge or merge back in a very organic manner across the domain, time domain T. So the way we achieve this when we have data, this is basically the truth behind the observed data. So the dotted points here are basically, we'll assume, the data available to us. So how do we recover this underlying function, this behavior from data? So we are gonna model the functional fixed effects using mixtures of what are called B-splines. So here's a figure down below that shows the B-splines. So fxt is going to be modeled as mixtures of bkt, which is B-splines, and then associated coefficients beta kx. So there are capital K such B-splines, and then they're also indexed by this x, so that the dependence on x is also modeled. So we had in this paper a new model for the functional random effects as well, but again, for this talk, in the interest of time and simplicity, I'm going to only focus on the fixed effects. So the nice thing about B-splines, generally speaking, is that they are locally supported. So for example, this B-spline function starts here and then just ends here, and then it's just 0 for the rest of the domain. This B-spline starts here and then it becomes 0 for the rest of the domain, and so on. So this would be very important for our purpose. So here's an illustration of how we can achieve that local behavior. So in this case, I'm showing a scenario when we don't have local behavior. So here we have beta 1 and beta 2. Beta 1, again, are these coefficients associated with x equals to 1. And beta 2 are, again, these coefficients associated with the value x equals to 2. So here we have a scenario where the values of these coefficients are same. And therefore, the two functions that we see, they have the same value throughout the entire domain. So if you look at, equivalently, if you look at the partition of x has two values here, 1 and 2. So they are basically clustered together for each knot point. Here I have considered 5. Each B-spline, basically, here we have considered a total of 5 B-splines. That's the idea. However, if we now consider a situation where beta 1 and beta 2, they take the same value for the first 2 knot points, or rather here for the first 3 knot points, sorry, and then they take different values, then this is the behavior that we see. So for the first part of the domain, the function is the same, but then they diverge, then they are different. Again, equivalently, if you look at the partition of x, it means that for the first few knot points, 1 and 2, these 2 levels of x, they are clustered together, but then after that, they are clustered separately. That's basically the whole idea. It's a fairly simple idea. So these are, again, the different generative steps. So you construct a basis function expansion of fxt, and then you induce, the next step is you induce a clustering of the coefficients at each knot point. So this is what we saw in the previous figure. And we do that by introducing latent variables, which we denote by z1x, z2x, and at the kth knot point zkx. So for example, if zkx takes the value small zk, then that coefficient beta kx here will take some value, beta k zk. So if for 2 different values of x here, if the value of zk is the same, then you have the same value on the right-hand side, so they get clustered together. So that's again the idea. And then if we are working with longitudinal data, that means we have to also take into account temporal dependence. So that's done by basically just connecting these variables, latent variables, using something called hidden Markov model. And then to induce, we don't need to pay too much attention to this complicated equation here. Basically, what it does is shown in this figure. So this induces a roughness penalty, basically. So if a function branches out, for example, here, so the black function has branched out into two other functions, a blue function and an orange function. So the coefficients at time point 6 are going to be centered around this black coefficient here. The same would have happened here. So at time point 15, the black and the orange functions march back. So the black coefficient here would be centered around the blue and the orange coefficient at the previous time point. So generally speaking, the idea is that children are going to be centered around their parents, and the parent-children relationship is determined again by this latent variable C1, C2, Zk. And then because we have multiple levels of X, we end up what is called, we end up with a graphical model like this for different values of X. And then finally, if we combine that with locally supported basis, we end up with a framework like this. So here I'm showing basically a recovery in that synthetic scenario. So you can still see the original two functions, black solid lines. And then on top of that, we have the recovered functions, which are slightly more weakly. The recovery, I would say, is pretty decent. And the whole thing is fully automated. All we need for the method to work is just the values of the y's and the x's and the time points at which they are observed. This whole structure, in which part they are constant, where they diverge, where they merge back together, it's entirely automatically determined by the method or by the algorithm. Now, in this case, we have again that original scenario. So X single covariate, 3 levels, 1, 2, 3, and then we have 20 knot points. So you can see that the total number of coefficients that we had to model basically is 20 times 3, because if we can look at this construction, we'd have 1 beta kx for each of the 3 different values of x, and then there are 20 different values of k. So in a completely unstructured model, the size of the model space would be 60. And the method correctly identifies which, where and how x is important and all of that. Next, we will consider, now that we have the basic ideas, hopefully, now that we have built some intuition behind the basic ideas, we are going to concentrate on a more complicated case of multiple predictors. So now we have x1, x2, xp, and the same idea, they may affect y differently in different longitudinal stages. So now the function, instead of being just indexed by x, is now indexed by x1, x2, xp. There are different possible combinations. And then the statistical problems are the same. How do you allow local inference of these conditional mean functions, and how do you allow them to evolve organically, branching and merging as necessary? So same idea, we'll construct first a basis expansion, and then we have to, the next stage, we have to reduce the dimension of the coefficients, because, so let's say we have just 10 predictors, so small p is 10, and then they have this different number of categories, 2, 3, 3, 2, 2, 3, 3, 3, and so on. And again, consider 20 time points. Now, if you calculate the size of the unstructured models, it's 5 million. So this is you can say, well, you have only 10 predictors. I mean, in this day and age, I think 10 predictor problem, nobody would call it a high dimensional problem. And if you look at each categorical predictor, they only have this many levels, but this becomes the size of the model space in the end. It's just, unless you impose some sort of structure, unless you do dimension reduction, etc., impose some sort of sparsity, it's just not possible to explore the whole model space. So we have to do that. We do that. So this step, the dimension reduction and local clustering, we do that using some technique called conditional tensor factorization. Again, we don't need to get into the math here. The basic idea is that you structure these coefficients as a tensor, which is sort of like higher dimensional extension of matrices. And then you do something called a Tucker tensor factorization. So you represent these beta ones basically as sort of like additional mixtures of these core tensor atoms, the beta stars, and some additional mixture level parameters, Z1, Z2. So here we are showing a 3-dimensional situation. This tensor is, of course, a 10-dimensional tensor. And then you have to do that. The challenge is that you have to do that at every, because we are dealing with longitudinal data, you have to do that at every not point, and then somehow you have to model the dependence between them. So previously we had hidden marker models. Now we have multiple variables x1, x2, xp. So now we have what is called in the literature a factorial hidden marker model. And then we'll induce roughness penalty. The equation gets a little bit more complicated, but it's the same idea. The parents get centered around their, the children get centered around their parents. And then finally, if we combine all of this with locally supported basis, so here, just for a change, I'm showing linear B-splines as opposed to quadratic B-splines. If we do that, then that gives us a framework like this again. So this is again synthetic data. Only two variables are important, x1 and x3. There were a total of 10. Remember, it's the same example that we just talked about. And this is now the behavior of this function fx1, x2, xpt. Up to a certain time point, they are all the same. Then they merge out, and then two functions again merge back, and so on. And then the model again completely eliminates the redundant covariance, and it calculates. So here in this figure again, we have the underlying true black lines, and on top of that, I have actually superimposed our fit. But the fit is so good that it's barely discernible. So the model has figured out completely automatically what's going on here. We had some. This is a fairly complicated framework, so we are not able to prove any red results, but we had some consistency results. We were able to show that our model consistently estimates the underlying functions and also does consistent variable selection at each of the nodes. So this was the first part of the talk. This was joint work with, he was my first PhD student actually, Giorgio, and my colleague here, Professor Peter Moore. This paper was accepted last year. Well, actually, I think this was just assigned to an issue. Maybe I should update this slide, but it was just assigned to an issue this year. So that's the first part of the talk. If anyone has any question on the first part, I can maybe take a break here. If not, I can move to the second part. No? Okay. So here's the second part of the talk. So I started thinking about this local inference framework when I was actually a graduate student, but then I got distracted by other interesting problems and never really did anything about that. And it is this applied problem that sort of motivated me to go back and take another look at that framework and develop like general ideas, etc. So this was a collaboration with the neuroscientist here. They study how the brain processes different sound categories. And they study in particular tonal languages, and they study Mandarin. Mandarin is a tonal language, and English is not. A tonal language is a language where the same syllable, the same word, if pronounced differently, carry different meanings. So here, for example, we have four different, here, for example, we have same syllable all sounding like ma, and depending on how it's pronounced, it can mean mother or hemp or horse or a rebuke, things like that. Now, neuroscientists think that native tone speech categories are generally acquired during the first few years of life when we are just learning our mother tongue. This is called a phonetic sensitivity period, and they want to understand how this neural commitment to native language speech sounds early in life, how this might affect the learning of novel speech categories in adulthood. By studying the acquisition of Mandarin tones by English-speaking adults, because English, again, is not a tonal language, so they are interested to see whether English speakers can handle, English speakers can learn Mandarin tones later in life. So this is an experiment that they did in the lab here in Austin, Texas. So they have these four tones. So they have 20 participants, and then they will hear these tones, and then they will basically give an answer. Well, that was the first tone, or the second tone, the third tone, or the fourth tone, and so on. And then they will be given corrective feedback. Yes, you were right, versus no, you are wrong, like that. So the structure of the data looks like this. So you have our training blocks T, and then we have I for the subject again, I subject. L is trial number within each training block. S is the input tone, and then D is the decision or the response category, and then tau is the time that takes these people to basically arrive at the decision. So if you look at the first trial here, the input tone was tone 2, and then this participant said that this was tone 1. So this was basically incorrectly identified as tone 1. So that's why these are in red. The second trial had input tone 3, and the participant said, yes, it's tone 3. So that was correctly identified, therefore shown in green. And then in the first trial, the participant had taken 1.2 milliseconds to answer the question, and the second one, 1.2 seconds to answer the question. And the second one, the participant took 0.9 seconds to answer the question. So on. So we have to, the idea here is the main challenge here is we have to build a joint model for this data, D and tau. When we say joint model or later marginal model for D, we'll assume implicitly that S is just the input tone, it's just part of the design. There's no real stochasticity in S. So we'll assume throughout that all of these things mean conditional on S, again, input tone. So this is how the response category answers look like. So here on the x-axis, you have the training blocks. And then each panel shows basically one input tone. So this is input tone, tone 1, input tone, tone 2, input tone, tone 3, and input tone, tone 4. And within each of these subpanels, the different responses are shown in different colors. So tone 1 response is always shown in red. So in this case, you can see that the input tone is tone 1, and the response tone is tone 1. So people, as they're getting trained, they're getting better and better at identifying tone 1 correctly. The same here, the input tone is tone 2, and the response tone 2 is also shown in blue. And here you can see again, as they are getting more and more training, they're getting better and better at identifying this tone correctly, and so on. Same with all the other, the remaining two subpanels as well. And then here, so we have data on two different variables, right? One is the response category, and the other is the response time. This is, again, what the response times look like. Here, I'm not showing individual heterogeneity because it's very highly variable. The y-axis basically becomes very large. So we're only looking at the average across different subjects for clarity. And then the question is, how do these stimuli affect the perceptual mechanisms at different longitudinal stages of the experiment as the participants become more and more experienced in this task? Now, so when I was first introduced to this area by one of the postdocs in their group, Fernando, I was fascinated by how they model this computationally. So neuroscientists think that if you look at these first two bullet points, this is how evidence gets accumulated in the brain and a decision is made. So evidence is accumulated basically by increased firing of neurons in the brain, and a decision is made when firing rates reach a threshold. And then if you look at neuroimaging data, spike train data, things like that, then once the decision is taken, then the neurons go back to sort of like the baseline level. So the electrical activity stops. So you can actually see this in neuroimaging data. And then some very clever computational neuroscientists have figured out that they can use drift division models to basically mimic this procedure, computationally speaking. So in drift division models, they would assume that evidence is accumulated over time via a drift division process, which is just a Gaussian process, Brownian motion. And then a decision would be made when an evidence threshold is reached by the process. So here, if we look at the figure, we have the binary category case, and we have, I don't know if there's an internet speed lag with you guys, but then in some of the trials, you will see that the process is moving upwards and is hitting the red line. So that means in this case, the response would be red category. And then in some other cases, it's hitting the blue line. And in that case, the response would be the blue category. And the time this process takes to hit basically any of these boundaries, that would be our response time. So I think it's pretty cool. And there's huge literature on this, hundreds of papers. However, well, before I get into that, let me first actually describe the race model. So race model, this is slightly different. So here we have one single process moving in a two-dimensional space. It's either hitting the line above zero or hitting the line below zero. But in race models, they assume that there are two independent processes for each input category, and they are moving like this. And then the process which hits the corresponding boundary first is the response category, and then the time it takes to reach that boundary is the response time. So slightly different, but anyway. So I said the literature on this models is huge. However, almost everything is focused on simple binary choice tasks. Only a very handful of papers existed on multi-category tasks, and everything is based on simple fixed race model. I found 0 papers on mixed race models. And then everything is based on a simple static study design. We have a longitudinal study design here, if you remember the experiment again. And then everything is based on a simple global inference framework. There are 0 papers on local inference frameworks. And again, why is that local inference framework that I talked about in part 1 of this lecture, why is that, or the seminar, why is that important here? Because if you think about it, you go back to this figure again. Initially, when people are getting introduced to these different tones, the brain has no idea what it's doing, which tone is basically which, right? So all these underlying differences in these processes will emerge basically as the process of learning itself. So if you think about this again, in this longitudinal experiment, in the first few training blocks, you don't really expect to see a lot of differences, but differences will emerge, things will diverge later on as an outcome of as a result of learning itself. So that's how local inference is important in this sort of problems. So in our motivating study, of course, this is very important because we again, just to reiterate these 4 points, we have 4 tones. We have longitudinal study design. We have significant also subject-specific heterogeneity, a lot of very good learners and some really bad learners. Additionally, I just explained why it's important to understand local inference, local differences between these processes. Early on, we don't expect to see any differences, but later on, differences will emerge. It's the process of learning itself. So this is how we do it. So again, this is a race model you can see. So we have 4 tones and 4 input tones, and therefore 4 possible decision choices. So we assume that we have 4 different Brownian motions running in the background corresponding to those 4 input tones. And they have their boundaries, which are denoted again by these parameters B. And then the process that hits the boundary first basically gives rise to the response, and the time it takes to reach that boundary is our response time. So here I'm showing a situation where the input tone is tone 1, so the red tone, and the red underlying process reached its corresponding boundary first. So that means in this particular trial, the decision was correctly taken. Anyway, now, so there are 3 different parameters in this model. The first one is the offset, which represents time basically relevant to any decision making. It's just like the time taken to press the computer button and things like that. And then the parameters that are of primary interest are the drift parameter, which represents the firing rates of these neurons, which are in this figure sort of represented by this line, these dotted lines here. So the larger the drift, basically the faster the process moves. So basically the higher the firing rates of the neurons. And then the other ones are these boundary parameters, which are shown here, the horizontal lines. And these represent the amount of evidence needed to decide in favor of a particular decision category D or BDS. It's the amount of evidence needed to decide in favor of D when the stimulus is S. So again, the nice thing is, if you look at this, all these parameters, delta S, mu ds, BDS, they are all biologically interpretable. So that's why these are so popular in computational neuroscience. And also, for our problem, the nice thing is in race model, time tau d to reach the dth response boundary under the stimulus, it is distributed as an inverse Gaussian with this PDF. So this has a closed form distribution. So here, for example, again, we have input on 1. And if you run many trials and consider different possible values of mu and b, which are shown here, these are the different types of distributions for the response times that you can get basically out of this trial. So it's inverse Gaussian distribution is fairly, it's a parametric distribution, but it's still fairly flexible at least for the purpose of modeling response times. Now, we have 4 different processes. If you again remember this figure, we have 4 different processes simultaneously running in the background, and the one that reaches the boundary first results in the decision outcome. So that means in the end, we only observed the time taken by this red process here to reach the boundary. The other ones are still running in the background, right? So that means if you look at the likelihood function, it will look like this. The joint likelihood function for each trial, that is. So you will have one, so here we have input tone S, we have decision category D, and there'd be one observed response time for the decision taken, the process which has reached its boundary first. And for the other ones, we only know that they are still running in the background. So they still haven't reached their decision, the corresponding decision boundary. So this is just the PDF of an inverse Gaussian, and this is therefore just 1 minus the CDF, basically, because it's still running in the background. We only know that for those other processes, the time to cross the corresponding boundaries are at least tau, so greater than tau. So that's why 1 minus the CDM, that's it. So now we can construct, we have everything we need to construct a likelihood function for our very complicated longitudinal experiment. It's just conditionally everything is independent. It's a nice thing about a hierarchical framework. So you just take a product of all these things. So you index these parameters, theta ds, which include again this bds, this mu ds, and also delta s collectively together. So you index them all by I, because they vary between individuals. You index them by time points, the plots. So these things on the x-axis, because they're evolving over time. And then in the likelihood function, you also have an index for trials. So you allow your parameters to depend on these DS combinations, the input tone and the output response, the individual, and the time point. Basically, that's it. And then so these are our parameters again, mu ds, the drift parameters, bds, the boundary parameters, etc. So if we say that this combination d comma s, so d takes 4 different values, tone 1, tone 2, tone 3, tone 4. S takes 4 different values, tone 1, tone 2, tone 3, tone 4. So if we say that x is the combination, factorial combination of d comma s, x now takes 16 different values, right? 4 times 4. And then if we write the same mu d s t I here, just replace d comma s by x, we are now basically back to the framework that we had discussed in part 1 of the seminar. This exponential function is only there because these parameters are positive. Both the drift parameters and the boundary parameters are positive. But other than that, if you look at this function, this is just our locally varying functional mixed effect, functional fixed effects that we considered in part 1. And these are the random effects. And then we can do local inference just the same way we discussed in part 1. So we're going to consider mixtures of B-splines, and we're going to locally cluster the coefficients and so on. We can do the same thing for the boundary parameters as well. Exact same thing, except that now they are just indexed by B rather than mu. That's all. So these are the results. So again, panel A shows the original data, panel A and B. So again, the accuracies obtained by different participants in this task and the associated decision times. And then in panel C and D, we are showing parameter estimates. So panel C is showing the drift parameter estimates, the mu's. And panel D shows the boundary parameter estimates, the B's. So you can see that basically the drift parameters are increasing over time, over training, basically. But if you look at the y-axis, so the y-axis here is from 0 to 2. But if you look at the y-axis for the boundaries, it starts basically from 1 point, basically at 1.5. So the y-axis here is from 1.5 to 3. So, and also if you look at these two particular sub-panels, the boundaries basically remain fairly constant over time. This was scientifically quite interesting. It tells us that it's mostly changes in the drift parameters. It's mostly changes, biologically speaking, in the firing rates of the neurons that basically cause learning. the amount of evidence required to come to a decision remains fairly constant over time. That doesn't change much. We did local inference, like I was telling. So here we are showing results of, here we're showing co-clustering probabilities, basically. So in each row, so remember we have these figures here. So basically, we are only focused on the correct decisions. So we are comparing these parameters with these parameters, with these parameters, and these parameters. So we have 4 different panels. So it's 4C2, 6 possible choices. So 1 and 2 basically means we're comparing mu11 and mu22 and B11 and B22. So the drift parameters and the boundary parameters. When the input tone is tone 1 and correct decision was taken as tone 1, and when the, for the first flow, that is when the drift parameter, when the input tone is tone 2, and again the correct decision is taken as tone 2. So 1 and 2 means basically we are comparing theta D1 D1, so theta 1 1 and theta 2 2 over time. So again, we can see for the first few blocks, so these are co-clustering probabilities. So for the first few blocks, this is a spurious block, we can't explain this. But other than that, for the first few blocks, the parameters are clustered together, which you would expect because the brain is still learning. But later on, differences emerge. And interestingly, 1 and 2, the parameters associated with the combinations 1 and 2, they are still clustered together. And 2 and 4, they are clustered together. But 1 and the other combinations, basically, they are not clustered together anymore. And this is again consistent with the biological information that our collaborators had. 1 and 3 are somewhat similar, so they are a little difficult to distinguish between. And 2 and 4, tone 2 and tone 4, likewise, are a little similar to each other. They are a little bit more difficult to distinguish from each other. Anyway, so this was again joint work with Giorgio again, and then Fernando is an assistant professor here at UT now, and my collaborator Bharat II, who is the chair of the communication sciences department at Northwestern now. In the interest of time, I think I'm running a little behind, so I'm going to skip the next part. I'm going to only discuss the problem, but not the solution. So the problem now is that this whole thing that we just discussed, it's a joint model for these two things, these two variables, right? It's the decision categories and decision times. Sometimes what can happen is you will not have good data on decision times. So this happened, for example, in the middle of the pandemic. So what happened during the pandemic is my collaborators, they started running these experiments online. So let's say somebody is sitting in Chicago, or I don't know, New York, blah, blah. They are sitting in front of their computer and then they're hitting these buttons. So you still have good data on their final response categories. But then because they're not monitored in a controlled experimental environment, you don't really know what they were doing in the process, whether they are watching something on the side, blah, whether they're drinking something, blah, blah, all these things. So response times, data on response times are no longer reliable. And another scenario, so sometimes they're interested in also studying pupillometry because it's a measure of cognitive load, meaning if the brain is exerting a lot of cognitive pressure, our pupils dilate, and if the brain is in a relaxed state, the pupils are small. So sometimes they measure this, and the problem is that this interferes basically with the process of hitting the button, the computer button itself, basically also changes pupillometry measurements. So what sometimes these experimenters, these neuroscientists tell their participants is to delay their responses. They usually ask them to delay them by 4 seconds or so. So delay approximately 4 seconds. So delay their responses. So that means, again, you basically lose. You don't have good quality data on the response times anymore. And then the question was whether it is possible to fit distribution models to data on response categories alone. So that was another problem that we tackled. We didn't to get into all the details there. But we didn't do local clustering yet because we don't have data on response time. So we didn't think that looking into all these underlying parameters at such depth and such fine detail would be reproducible. So we just played it safe and we did global inference. But we saw similar things. We saw that tone 2 and tone 4, the parameters associated with them were clustered together. And tone 1 and tone 3 parameters associated with them were clustered together. Broadly speaking, the final answer is you can recover some of the underlying features, but not everything. If you don't have data on response times completely missing. And this was joint work with Minerva and a student in Bharat's lab named JC. It was published in Psychometrica last year, or actually this year. And then this is the last part I'm going to talk about. Again, if anybody has any question, etc., just speak up. So the last part is going to be on a very different application. It's still neuroscience motivated, but it's not behavioral neuroscience anymore. It's neuroimaging. So this is a well-known fact that brain functions are very localized. Certain tasks are basically controlled by certain small parts in the brain. And if you remember again, the idea of local inference is almost ideally suited for this type of problems, right? So all those things that we did for behavioral inference, we replicate them for this type of data, neuroimaging data. But now the domain over which the variables, the different predictors can have different influence is basically the whole brain. So now the domain is no longer a time domain. It's basically a complex 3D spatial domain, right? The whole brain. So this is not the study that motivated this research, but it's simple enough to be able to present in a talk that has so much other materials to cover. So it's a binary task. So you basically, participants see these arrows on a computer screen. So if all the arrows point in a particular direction, then it's called congruent. If the arrows point in different directions, like in this case, incongruent. And then the idea is, then the problem is you have to find out which parts of the brain are basically responsible, in making this happen. So yeah, it's a very similar idea very similar idea at the basic level. So you would introduce cluster membership atoms, now not for different time locations, but different spatial locations. X is again your input stimulus. So in this case, in this experiment, X takes value either 1 and 2, depending on whether people are seeing congruent arrows or incongruent arrows. And then depending on the values that these variables take, some parameters basically get clustered together, and it's a local clustering. So previously we had used hidden Markov model. Now we are using something called hidden Markov nanofield. And then we'll impose a spatial roughness penalty so that things look more or less homogeneous across vast swaths of the spatial domain, because voxels which are right next to each other, they behave similarly. It's only certain small regions where you expect to see the signals. So at the basic level, this is a similar idea, but hidden Markov nanofields and hidden Markov models is totally different. Statistically speaking, computationally speaking, theoretically speaking, they're totally different beasts. So this took us quite a while to figure out. We are still working on. We are now wrapping up the paper actually, but the results are quite promising. So here we have 3 different figures. The left-hand side is basically just voxel-wise analysis, the traditional way of doing these things, and then the one in the middle, that's false discovery rate corrected, multiplicity corrected results, which is decent. But then if you look at the results on the right-hand side, that's what we have obtained using our method. And it's a much cleaner picture. It almost like completely eliminates all the noises and just pinpoints the locations of the actual signals. So this is, from what we understand, this is pretty promising and exciting. So this was joint work with another PhD student called Blake, who's really good at computation, almost a wizard on the computers. And then another postdoc from Bharat's lab, Kevin, and my collaborator from University of Florida Biostatistics, Sarkar. So I'm going to wrap up now. So I talked about local inference problems, which broadly defined are problems where you have a bunch of predictors and different sets of predictors. They can be important in different parts of S, and the same predictors can have different influence in different parts of X. And we considered 3 different examples in this talk. The first one was the general framework, which is longitudinal data that we discussed in fairly good detail in the first part of the talk. And then we saw an example in grid division models, where again, initially, you don't expect to see any differences, but differences emerge later on as a process of learning itself. And then this third example, which I didn't get the time to discuss in detail, in this one, we didn't have data on response times. So we actually didn't, in the end, do local inference. So even though I'm very excited about the local inference framework, the point there is that we should not be just blindly applying local inference just because we can. We have to be mindful of the practical side of things, whether the results are going to be reproducible, things like that. And then the fourth example was the one that we just discussed, the new imaging example. In that case, the space S is basically a 3D space, the brain. So this is nice. Local inference problems are not the only problems I'm working on right now. There are others. Again, like I said, local inference problems. You should not be doing local inference just for the sake of doing local inference. There are many other problems, many other methods where local inference may not be needed. But if we are focused on local inference problems, they are pretty much everywhere. And I have, Subrata mentioned at the beginning, I have some other interests in nutritional epidemiology, vocal communication neuroscience, application domains. I have also some interest in analysis of music. Recently, I'm working with another colleague of mine, is an expert in air pollution. There are local inference problems are pretty much everywhere in all of these domains. So in that sense, I think it's an important set of problems that's going to keep me busy for the next few years at least. That is all. Thank you again for the invitation. Hope it was interesting at some level at least, and it was very nice to be doing this in front of my former classmates and my former respected professors.
Thank you, Dr. Sarkar, for this interesting presentation and for making time from your busy schedule. So, are there any questions from any audience? I think there are no such questions.
Yeah,
One
just one question. Yeah, Dr. Sarkar. I'm Samrat. That's the local inference problem. Is it quite similar to the? It's not maybe the similar, but it's a legal type, the local optimization problem, or like that, or something different from that. In optimization, there's some local optimization. Then, for going for the global optimization and so on. So, yeah, in local optimization, we have to achieve a certain level of optimal. It may not be the global optimal, it may be the near optimal. Then for searching for the global, the better one for that, so we have to achieve the global one. So that's the local optimization problem. Initially, I'm quite satisfied with a certain optimality. So that's the local optimality. So is it this less the local inference? It's similar like that local optimization.
Well, there might be some broad similarity, like the way you explained it, but then local optimization is mostly an implementation procedure. And then what we are developing, what we are doing, these are statistical methods. For example, you can, I don't know, a computation. I didn't, again, in the interest of time, I didn't get into any of the computational methods that we used or developed to be able to fit this type of complicated models that has to explore a very complicated model space and figure out what's going on. But what I'm trying to say is, if you have a local inference problem, in principle, you can probably also use local optimization methods to basically So you see what I'm trying to say. So one is what I'm talking about is a statistical problem. What you are talking about, based on my understanding, is a computational technique. How do you
Yeah,
figure out which? Yeah.
yeah.
So that's the only similarity
Yeah, okay.
I can think of at this stage.
Okay. Thank you. Thank you.
Yeah, thank you for the question.
Where do these local inference problems arise in air pollution modeling?
Yes, thank you, ma'am. So this is a relatively recent. So I had presented this formally, informally, talked to my colleagues around in the department, and we have a colleague here. Well, he just moved to Brown University, Professor Corey Ziegler. He does air pollution problems, and he studies causal inference questions in there. So there, the problem arises because you can potentially think of a situation where you have some confounders, and they are only important in certain, let's say, part of a spatial domain again. So maybe there are some confounders which are important in Texas because of the hot weather here, etc. But they are not important, let's say, in Michigan. So again, if you look at the entire spatial map of the United States, you'll see that some confounders, covariates are important in certain parts of the continental USA, but not across the whole of USA. So that's how local inference problems arise. I'm talking at a very broad level, but there could be many different variations of this basic formulation, but broadly speaking, that's how local inference problems arise in air pollution. Or rather, causal inference in air pollution.
Looking for in spatial.
Um, I couldn't hear you properly, Subrata. Can you please repeat the question?
The spatial data, and we want to some appropriate to find out the spatial heterogeneity and the appropriate that causal relationship between the response and the predictors. So is there any role of local inference for that spatial modeling?
I don't know. I mean, how would that be very different from this air pollution problem I just described?
Actually, from that questions, these questions arise in my mind.
Yeah, I don't know, Subrata. Sorry. Now I'm just. I mean, the local inference framework is a very general framework. I mean, you can study this if you have some interest in just studying mathematical statistics, mathematical results. You can just study it as a separate general framework and then figure out where you can apply it. So in that sense, it should have very broad applicability in many different domains. It's a very simple idea, right? Different sets of predictors influence different sets of predictors influence your variable interest in different parts of a functional domain. It doesn't always have to be actually a functional domain. It can also be discrete in certain cases. So I guess the answer is yes, but then I don't know the details at this stage.
Okay, thank you, Abhra. Is there any other question? So thank you once again, Dr. Abhra Sarkar, for making this time from your busy schedule and presenting this interesting presentation. Thank you.
Thank you.